Let's see. Okay. Hi, everyone. Thank you all for coming here. This is a very tight-knit kind of talk, very intimate, very nice. My name is Guillaume. I'm a PhD student at UPFL, and I work on Dotty. And today I'm going to talk to you about Dotty and say a bit about how it works and what the sort of things we're planning, and then dive into the internals of a compiler and hopefully get you excited about trying it out or even contributing to the compiler. All right, so what's Dotty? So Dotty is this new experimental compiler for Scala that's been in development for a few years, at first just by Martres and Odersky, and now we are a small team, and development has picked up pace in the last year also. The main goal of Dotty, I'd say, is to have completely redesigned internals of the type system, but the language itself feels very familiar from like a user point of view. And incidentally, because we are kind of rewriting everything from scratch, we get to redesign components that have been existing for ages and that kind of work, but were not extremely well working. For example, we had to completely rewrite the integration with SBT to get incremental compilation working, which is a thing that has existed for a long time, but hadn't got much love. And by doing that, we are able to get SBT to stop forgetting to recompile things that it should forget, and hopefully work in more cases. Another example is that we have a new pattern matching exhaustiveness checker. So it's the thing that warns you when you have a case class in a trait and you forget some case in a pattern match. And the new one is much simpler and much faster. And hopefully it works better, but we only have tested it like on a bunch of test cases from the old compiler. And the interesting thing is that some of this stuff might be ported back to Scala 2 yet, because Scala 2 is still in active development, and these things are completely new design, but they're not specific to the new compiler. So one of the things you're probably wondering about is, well, can you actually do things with Dotty right now, or is it just a dumb compiler? And so as I said, we have SBT integration, including incremental recompilation, so that's a big plus. And we have very basic IntelliJ support done by the IntelliJ folks. If you try to use Dotty features, like the type checker of IntelliJ isn't going to help you because it doesn't know about Dotty features, but it can compile code with Dotty. And we have a guide which explains how to do that. And we have a REPL, so you can actually try it out easily and get feedback. We don't have a presentation compiler. The presentation compiler is the thing that an IDE like Eclipse or Enzyme communicates with to type check your code and gives you information on errors, that kind of things. And that's a pretty big piece of work that we don't have, and until we have that, like IDE integration is going to be very limited, except maybe on IntelliJ side where they do their own thing, which is completely independent of our compiler, but that remains to be seen. Right, by the way, you can interrupt me at any time because I think we have a bunch of time.
Oh, I just had a question about the SBT integration with that incremental recompilation. Are you also trying to get that to work with other build frameworks like Gradle?
We are not, but the SBT folks have done works in splitting the incremental compilation part of SBT, which is now called Zinc from SBT itself. So this already exists and it's used by CBT, among others. And it's getting a lot more work now in SBT 1.0. So hopefully I have to do nothing and it will just work at some point. Until then, you have to put up with SBT or maybe use CBT. So I don't think anyone has tried to compile stuff with CBT and Dotty, but feel free to try and see what happens. So I'm going to try to talk about the future, which is always difficult. So Scala 2 is like here to stay for a long time. It's like there's a sizable team behind Scala 2 at Lightbend working on the compiler, and they're doing great work, and their like 2.12 is about to come out with Java 8 support and a bunch of other nice things. So like shouldn't worry too much about that. And Dotty itself probably won't be production ready for at least a couple of years, assuming that like it's successful, since I still think of it as an experiment. So migration is complicated, but basically we'd like the two compilers to converge as much as possible. So far we haven't tried to compile that much Scala 2 code with Dotty. We have compiled most of the standard library already, so we support a lot of things. And to do that, we have a compatibility mode where we enable some things that we want to remove from the language, but that we still want for compatibility. And on the other side, Scala 2 is going to implement some features that have been prototyped in Dotty, like thread parameters that I'm going to talk about a bit later. Macros. So we're not going to get macros as they are in Scala 2 because macros in Scala 2 are way too tied to how the compiler works internally. They're basically the internal representation of the compiler. So there's no way that we can get that to work on Dotty. However, basically the long-term plan is to have macros based on Scala meta. And if you're interested in more details on that, there's now a prototype of that on GitHub by Eugene Burmarco. And he has a talk at Scala Days where he explains that in more details. So if you're interested in macros, you should watch that. Until then, we think that if it makes sense, probably the best thing we can do is to take macros that people actually use, like common, very popular macros, and put them in the compiler itself, if it makes sense, which like has to be determined on a case-by-case basis. We actually don't have a very good idea of which macros are very popular and that kind of thing, so that remains to be researched. And the other thing that could be done is compiler plugins, which are less involved than macros, but we don't have any compiler plugin yet, and no one has expressed any interest in writing them, but we welcome people trying that out. I think that's maybe an interesting way to do things until we have macros. Back to compatibility. So we have a rewriting tool, or a very basic version of a rewriting tool. Basically, when you compile your code with Dotty in the Scala 2 compatibility mode, you can pass a -rewrite option, and Dotty is going to rewrite your code for you. It's like very small changes it's going to do locally to get some things to type checks that wouldn't type check in Dotty. And we'd like to get this to cover much more cases, to like cover like potentially every difference we can in type inference, that kind of thing. So the Scala Center is going to have one person working full time on this rewriting tool starting very soon to make transition as smooth as possible. Yes?
On the last slide, just before we get away from the compiler.
Oops.
Does Dotty support as the same level of compilation levels as Scala C, or are they completely disconnected?
What do you mean by compilation levels?
Like there's like 20 or like 15 or 20 different stages of compilation in Scala C. So are they mapped one-to-one, or are they just... You
mean the compilation phases,
yeah,
like typer, erasure, that kind of things?
I'm wondering about the compiler plugins in particular. So would we add another...
So, okay. So the question was about compiler phases. The compiler is split into a bunch of different phases that take as input a tree that represents the program and transform it. And so Scala C has its own set of phases, and Dotty has its own set of phases too. And I'm going to talk in more details about that in a minute. But roughly, we have similar things in that at the beginning you have type checking, in the middle you have erasure, at the end you have the backend which generates bytecode. In the middle you have a bunch of stuff. this stuff is different between Scala C and Dotty.
Also, I think I've heard like 50 phases in Dotty versus.
Yeah, I have a nice
so it's
diagram.
There's no isomorphism.
Like, don't be scared, but I have a nice diagram. I'll show you.
What's your take on implementing popular macros as a language features? I'm a bit afraid that it might. Well, I'm not afraid, but aren't you afraid to kind of like grow language too big?
Yeah, which is why I said if it makes sense. So that's a very big if.
I'll ask another question. Who decides if it makes sense?
To implement features in Dotty.
Yeah.
So we don't have a formal process to implement things in Dotty, like Scala C has the SIP process.
Yeah.
We might, if it's needed, get something similar for Dotty specific things. For now, we put issues on GitHub and people discuss, and based on that, we do whatever we should do. So it's very informal because we haven't had to worry too much about it. If more and more people start wanting to contribute and that kind of things, we might need to make the process a bit more formal. For now, I think that like we discuss things and figure it out is okay.
Yeah. Okay. Cool.
How many contributors are there today?
How many contributors to Dotty? If you look on GitHub, I think it says 23. That includes people who like fix a typo or that kind of things. So, but if you're speaking of active contributors, I think we have less than 10 people working on it regularly. Sometimes I joke that we should pretend to be a JSON library because that seems to be the thing that gets the most contributors.
Are you going to talk about the Dotty calculus here?
Nope. I'm not going to talk about type theory.
All right.
Just practical stuff.
Is Scala.js, how does that fit into?
So Scala.js has a very experimental backend for Dotty, which basically can compile Hello World. And so it's a proof of concept, but we can get it to work. And for now, not many people work on Scala.js, basically 2 or 3 people, and they're focused on making it work as best as they can on Scala C, and they're doing great work on that. So eventually we'll have Scala.js on Dotty, but probably not soon, unless people start contributing because they're interested in that kind of things. There's probably lots of low-hanging fruits here, but I couldn't tell you because I've never actually looked very much into the internals of Scala.js.
And how soon will you have like all the major features, at least in some stage of completion, maybe bugs, but implemented?
Your question is about which major features we have now in Dotty?
When will you have like all of the major
Oh.
features for like the first milestone implemented?
So the first milestone was that we got the compiler to compile itself. So the compiler is written in using, like it compiles with the current Scala compiler, but it also compiles itself. It bootstraps. So that means that we have already implemented a bunch of features.
I remember Martin's talk on effect system there.
Oh, so like crazy ideas like effect systems or every other things that we have proposed, we have no milestone at all on that.
Yeah, but currently scheduled features are already there. You're just figuring out how to make it work nice.
So we are still very much focused on making it stable and making it work on more and more code. So at this point, we have tested it on very little code that is not the compiler itself, mostly the standard library. And I think that's going to occupy us for some times. And then we'll be able to do some sort of alpha release or something. And we'll focus on more crazy features afterwards.
Yeah, because basically the question is, if I will have some piece of code, when I want to try to compile it against Dotty, I want to be sure that it's actually to learn what sort of things changed. I want to be sure that it's all of them for the first stage.
So the things that we change.
When probably your guess, like when will we have this alpha, like half a year, a year? Just very high level, like a couple of months.
Like couple of months maybe, hopefully, like if we are being optimistic.
More realistic, like a year.
It's very hard to say because it depends on what we end up discovering as we try more things.
Okay.
But like if you try Dotty now, the things that it's going to like reject, the thing that it's not going to allow you to do, I don't think this is likely to get bigger. Like we're not going to break more code that we're breaking right now.
So
but we are
makes
likely
sense
to
try something already.
Yes, like taking in mind that it's very alpha quality and a very early product. Yes,
Want to,
like
have some
if you have some code that compiles now with Dotty, it's likely to continue compiling in the future. Like we compile Dotty with Dotty, and we hope to continue doing that. So
that's such a trivial piece of code.
well, it's a compiler. It's about 50,000 lines of code, so it's not a humongous project, but it's pretty big. It doesn't use very advanced type level features,
Yeah,
but
I mean, that's not the trivial.
well, then I hope you contribute, because if it doesn't use like complicated things, it should be very easy to contribute to. But yes, I don't know. We'll see. Rewriting tool, yes, I think I have talked about that. Dropped features. Basically, there's not that much. There's procedure syntax and early definitions, and I'll explain what we replace early definition with a bit later. And existential types written using for some. So here's an example. In Scala 2, you can write array T for some type T. We don't support this syntax anymore because it allows you to do things which are more general than what we want to support, but you can still write array of bracket underscore is a subtype of foo. So I don't think that many people care very much about that. Like, who has used for some here? Do you think you can? Who has used the for some in types? Okay. Do you think you can rewrite it using wildcards, or did you use advanced for some?
Like F-bounded polymorphism.
Uh-huh.
So I'm not totally sure. I would have liked to write it in that syntax.
Yeah.
That's a lot less few
Okay.
characters. But I gave me type errors when I tried it, so maybe I didn't try hard enough.
Or maybe there was a bug in the compiler, but like, if you can dig up an example, that would be interesting.
Sure.
But we think that like most of the time you should be able to rewrite it using wildcards, so it shouldn't be too much of a problem for any sort of migration. Implemented features, so that's the cool stuff you can try right now, because it's actually implemented and not just planned or just an idea. So intersection types and union types are a neat thing. So basically you have two kind of things. You have A and B, which is a type. It's the supertype of all subtypes of both A and B. So if you have a class which extends A and B, then it's a subtype of A and B. If you have a trait or whatever that extends A and B, the same. It's similar to the existing type, which was A with B. And we have A or B, which is the type of things which are A or things which are B. Yes?
I once had the case when I wanted to pattern match against the conjunction and to use in the match
I'm going to talk about
some fields which are common
Yeah.
in the intersection.
I'm going to talk about that in a second.
Because IntelliJ was fine with that, but not Scala compiler.
So what's the difference between intersection types and compound types? Okay, so here is a somewhat involved example where you have an A, a B, something which has an A, something which has a B, and you make a subtype of has A and has B. So it needs a get method which is both A and B. And if you look at the type you get in Scala 2, the type that it infers, it's has A with has B, bracket, and get with A with B. Why does it add the bracket with the get A with B? Because has A with has B is not commutative, and like the type of get in has A with has B. So the first, that thing is just the type of get in B. So it's less precise than what you want. And like if you switch things around, if you do has B with has A, it's the inverse. So in Dotty, it just has A with and has B. Oh, there's a typo here. It's has A and has B, not A and B. And has A and has B has a member get, and the type of this member get is A and B, which is basically the thing you'd expect. Like when you do an intersection of two classes, the members, that type have the intersections of the members in each class. Union types. So union types are cool. Like you can have an if which returns an int or a string, and its type is int or string. And then you can pattern match on it to get a thing out of it. Yes?
Does this use reflection?
Nope.
Okay.
One sec.
On the right.
I have a different question.
Yes.
Is this like intended to be used to implement like algebraic data types? Still like sealed trait and case classes?
Algebraic data types are still sealed trait and case classes. You can use that when you have something which is kind of like an algebraic data type, but is not a sealed trait, which happens sometimes. And we might, I didn't talk about that, but we might implement an alternative syntax or something for algebraic data types, but there's no concrete proposal yet for that.
Sure. Is this meant to implement JavaScript?
It's actually probably useful. Yeah, TypeScript has union types. They kind of pioneered that one, and they do nice things with them. So it's probably useful for JavaScript. And what is interesting is that this is safe. Like if you do your match and you forget one of the case, you're going to get a warning because it's like a sealed trait. You know all the cases. That's very cool. Yes.
I'm just wondering the type of the if expression.
Uh-huh.
I don't know how it behaved previously, if it threw an error.
No, so previously you got the list upper bound of int and string, so that's the type which is the supertype of both of them, and in this case it's any,
Okay.
which means that you can do much with it except compare it with for referential equality. But the other cool thing you can do on a union type is you can select on it. So if you have two completely different class A and B with a member size with some type, and you have an X which has type A or B, then you can call X.size. And this does not use reflection. We just do an instance of check. This is just equivalent to that code. So if X is an instance of A, then we cast X to A and call size on it. Otherwise, we cast X to B and we call size on it. So you pay the price of a branch. And instance of is pretty fast as far as I know on the JVM. It's just checking like a flag on the header of the class. So don't be afraid to use that. But yeah, we don't infer union types by default. So that means that in my previous example, if I didn't put the type ascription int or string, X will get type any. We don't do that for basically two reasons. Like union types can be too precise, and if you like have some value with a union type and try to use it later, you might get some very complicated weird type error because things just don't match the way you expect them to match. This doesn't happen often, but when it happens, it can be confusing. So we turn that off by default. The other is that if you have many alternatives, like imagine you have some pattern matching things where you return a different kind of subtype every time, and you have 40 of them, then you get a huge type, and then the compiler has to do subtyping check. So if it wants to know if A or B or C or D is a subtype of something, it might have to do 40 different subtyping checks, and that can become wild. So we don't do that by default. However, for now, if you want to play with it, there's a language import that basically changes the compiler to keep these union types instead of replacing them by their upper bound. Yes?
Have you considered removing the any type?
And replacing it by what?
Nothing? Haskell doesn't have a top type.
Yes, because Haskell does not have subtyping. So why do you hate the any type?
As, just results in some like bad errors sometimes.
Mm-hmm.
Like poor inferencing, because things get inferenced to any, or in Haskell you'll get an error at the time of like where the error actually was. In Scala often you get the error like in a volume.
Yes. So the question is, have you considered removing the union types, because the any type, because sometimes you like have an error in your code that results in getting any when you'd rather have a compiler tell you that you're doing something wrong now instead of 10 lines later. No, we're not going to remove the any type because it's still very useful, but I don't see why we couldn't have some linting features or something you can turn on to warn you when you infer any type. And maybe we can infer unions in some places where it makes sense and have like less weird error messages in that case. It remains to be seen. Like, again, if you have like interesting examples of things that break in weird ways, you can post an issue and we can see if we can think of a better way to do things.
So the new feature sounds like a great solution to that. Like saying like, hey, like I inferred any here and I got a weird error, but here's where the error probably was, where I inferred any. So
getting the type checker to give you more meaningful error messages is a very interesting problem, but also a very hard problem. I don't know if we'll get there, but hopefully, yes. Like, Elm does very interesting things with error messages, where it tries to give you as much context as possible. I think we can do more. We can do similar things in Dotty. Other feature or trait parameters. So they replace array definitions, and if you don't know what array definition is, that's okay. You can forget about them and never care. But basically, when you have some trait with like side effects, when you create the trait, like this print call, and you have a class which extends this trait, if you try to call newbie, at the moment when the print is going to be called, X is still null, because the constructor of the trait is called before the constructor of the class. So array definitions are this weird syntax that allows you to bypass that by initializing things before calling the trait superconstructor. We don't support that syntax in Dotty and don't intend to support it. Instead, we have trait parameters, which are basically like class parameters. So in a class, you can, the primary constructor of a class is just the parameters you put after the class and the name of the class. And in Dotty, you can do the same for traits. There's a few restrictions because of the way traits work. You can look at the SIP25 document for more information, but basically it does what you want most of the time. Well, it does what you want, or it's going to give you an error because what you want is not possible. Yes?
So should we use traits every time, except when we can't?
Basically, if something is abstract, use a trait. If something is concrete, use a class. Abstract class is only useful for Scala, for Java compatibility. That's the way you should think about it. This is especially true now that we are based on Java 8, where traits have a much lower impact on performance and bytecode size than before, when we had to do a lot more work. When Scala C had to do a lot more work to make traits work on the JVM. Now it's much simpler. Literal-based singleton types are a fun thing. So the type of 1 is int, but 1 has a more precise type, which is just 1. In the same way that if you have a value x, you can x.type means the type where the only value is x. And that doesn't seem very useful like that, but you can do fun things with it, like combine it with union types and other things to make a list where you can have a string or 1. And if you go look at the SIP23, you have examples of more useful things. It comes up, for example, in JavaScript when you interact with JavaScript APIs, which take string as arguments, and there's only a fixed set of strings that they take, that kind of things.
So
this is compile time checked?
Yes. All of that is compile time. So one.
So for example, if you say list on the right-hand side, you say list of food 2.
Yes.
At what time would you have an error?
You'll get an error at compile time because the type of 2 is not a subtype of the type of 1. The type of 1 is a subtype of the type of int. So you don't have to care that the most precise type of 2 is 2. But
you don't infer those types either?
yes, so singleton types are also never inferred because if you do that, then terrible things are going to happen because you're never going to be able to, for example, mutate anything because everything will be it's a type which is equal to exactly what they are. So
Types for string literals.
yes, we have string literals types too.
And any object like case classes type, precise type for this case class.
More precise than what? So
like case class with a field which value is 1.
No, that's an interesting thing. We don't have that. But I'm going to...
I mean, is it just for primitive types? Or
yes, it's for literals. So literals are integers, strings, floating points, symbols. That's it. And also for every val. So if you have but that was already in Scala too. Like if you have an x, its most precise type is x.type. Yes?
If you have the keep unions imported and not the type annotation, will it infer?
Sorry?
If you have the keep unions imported and not the annotation type, will it infer this type?
So we never infer singleton types, even if we have keep unions. We're not going to not widen singleton types. We could have a keep singleton, but it's like not going to do what you want to do. Like there's no way. So I think you will have to live with type annotations, or like there are otherwise. Like for example, I think shapeless has a construct which is called narrow. So if you do narrow of some value, you get the singleton type inferred. But you have to put narrow in your code around your value. So we might do something like that, or let that be a library thing. So proposed features. So I'm going to talk about things that have been proposed but have not been implemented and might never be implemented, or we don't know, but this is the kind of things we're interested in doing but haven't invested much time in doing yet. So the biggest one is probably having an effect system, so being able to have a type for purely functional functions and have a possibility to propagate effects, to have polymorphic effects. The same way you have polymorphic types. You can say that you map over something and you keep the effects you had before the map, after the map. So this is probably like the main idea is to implement that using implicits. So when you have an implicit in scope, that means that you can use this effect, and the implicit propagates through your program. And so currently, when we use implicits, we have to pass values, and these values have to be present at runtime. But as part of this, we'd like to have a way to have implicit values which are only there at compile time to prevent you from doing things or allow you to do things, but have no representation at runtime, so that you have no runtime cost from using that. So there's actually a pull request done recently by Nicolas, which starts implementing that, these sort of phantom values. Generic programming, so if you're familiar with shapeless, how many people in this room have used shapeless? Okay, cool. So shapeless allows you to abstract over arrays, abstract over case classes, have lists, generate like heterogeneous lists, that kind of things. So we're interested in having similar capabilities. Like we'd like to be able to make functions that work on every case class that has a certain set of types as elements, that kind of things. This is again something that we haven't implemented at all, and but we think that it makes sense, and JPI shows that it's something that people really want and is actually useful. And non-nullable types, so I'm going to explain that in a bit more detail. So null has type null in Scala, and null is a subtype of every non-value class. So a value class is every primitive class like int, float, and every class that extends any val. So if you have a class that extends any val, you can't assign null to it. And what we want to do is make it so that you can't assign null to anything by default. So if you try to write val x colon string equals null, you will get a type error. And you can combine that with union type to make the type of something which is either a string or null. And we probably want to have a shorter syntax like a question mark to make this something that people actually want to use. Do you dislike the question mark? Or do you
It's just like making one moment more special than the others. Then you need a spaceship for lists and, I don't know, like elephant for futures or something.
Well, null is special because it's part of the implementation, and it's part of the base language, and it's not a library thing. It's really a language thing. And going for
language, Java?
Like the JVM, but also JavaScript. Also, everything which uses pointers has a null pointer. So we want to probably treat nullability as an effect. So you don't want to always use these question marks everywhere or the union null syntax when you're interacting with Java code, or just because you decide that you love null and you want to use it everywhere. So if you want to do that, you should be able to do that and have some way to turn on and off the non-nullability. And we don't want Java to become annoying to write, so you need some way to interact with that easily. But again, that's not something that we have implemented at all yet.
Is there like a not null annotation?
So in Java, there's an @not null annotation, and we could take advantage of that to avoid having to think that things from Java are nullable. I don't know how much people use that, because that must be horrible having to write @not null everywhere.
Standard library in particular doesn't use it very much.
Not a very fun Java having to add the annotations to everything.
I think null should be opt-in, not opt-out. I like that.
Okay, we are done with the first part, and now I'm going to actually talk about how things are implemented. So before that, maybe if you have any question.
Maybe some off-topic,
Uh-huh.
but I think about it. And are there any kind of like systems that don't have null reference nowadays?
Are there systems without nulls? Yes. Haskell doesn't have nulls.
Okay.
As far as I know, there's nothing comparable. No.
Rust doesn't.
So yeah, Rust has option types, and I think it's implemented when possible using null pointers, but it's transparent to the user. So we could.
Opt-in null.
What's opt-in? Sorry.
Like in Rust, I think you have to opt in to your type, including null.
Oh.
Like option. Like if it's an option type, you have to write. It's not that anything can be null at any test.
So
I
my.
actually don't know Rust.
Okay. No, what I thought was.
Reference is more like a runtime.
If you use an option of something in Rust, it has no runtime cost because everything is a pointer, and you can just represent the null case using a null pointer. So option is just or null, and we can't exactly do the same thing because like an option of option can't be represented using a type which is null or not null. but we could have like a nice API around the nullability thing, so you don't have to actually write null and still get the performance benefit. Yes?
So the compatibility with Java with this opt-in or opt-out and null, like how at the bytecode level, can you tell Dotty compiled bytecode from Java compiled bytecode, and
Yes.
you
So
enable nullability for all Java functions that don't have that type description or that annotation and not null?
So the question is, can we tell from the bytecode level if something comes from Dotty or Java so that we can decide what to do about nulls? And the answer is yes. In fact, if you just have the bytecode, Dotty doesn't know what to do with Dotty code because it looks like Java. When we compile Dotty code, both Dotty and Scala C do the same thing. We add extra information to the class files about the stuff that Scala cares about, but that is not representable on the JVM. So we do know where something comes from.
So libraries written in Dotty would know that their type can be nullable or can be not nullable?
Yes, potentially.
Okay.
Okay. Another scary picture of the compiler pipeline. So this is all the phases in the compiler. It doesn't really matter what the names are, but every line is a compiler phase, something that basically takes a tree, which represents code, and transform it. And as we go through the pipeline, the trees gets more and more simple and more closer to what we can represent on the JVM or another backend until we get to the backend, which is the part that emits JVM bytecode. So you start from the parser, which takes your source code and gives you an untyped tree. And then the typer is going to get you a type tree, and everything else works with type tree. The thing in the middle, which is the most important, is erasure. Erasure is the thing that is going to type check again your whole program, but after replacing every type by a type that is representable on the JVM. For example, if you have a list of int, the JVM doesn't know about type parameters, so you replace that by a list, and you compute the types of everything again. And so things which are after that behave in different ways of things which are before that. But it's all still basically Scala code, just Scala code with some extra constraints. And so to answer an earlier question, compared to Scala C, we still have a typer, we still have a pickler, a thing which is going to take bytecode and figure out to take the Scala code and put it in bytecode, like all the annotations, all the things that let us know that it comes from Scala. And we still have, of course, a backend. Actually, the backend we use the code is shared with Scala C. It's mostly shared with Scala C, so we benefit from what they do. And in the middle, erasure is also something that basically everyone on the JVM has to do. Java C also does erasure because it has also type parameters which cannot be represented on the JVM. Yes?
So regarding the backend, I heard that Dotty is going to have like a linker or some concept like that.
Okay, so the Dotty linker is a completely separate thing. The principle of a Dotty linker is it's a sort of whole program optimizer for Dotty. It's going to look at every library use, everything, and if everything is compiled with Dotty, it has a lot of information that allows it to do a lot of basically pre-optimization to make the code easier to optimize for the JVM. Mostly it's doing specialization because the JVM has a hard time with very polymorphic function calls, and it doesn't do a lot of function specialization. So the Dotty linker is another experimental project on top of Dotty, which is an experimental project. There's some nice talks about it if you want to learn more. It's not part of Dotty itself currently. There's a separate fork of Dotty with the linker.
So would that mean that some information that Dotty linker would use would be encoded in Java?
So the way,
so how would it be take advantage of?
Yeah, so the way the linker works is basically adds various phases in this giant pipeline to collect information about Dotty to be able to optimize things. And it also uses information from Tasty, So tasty is the thing that we put in the bytecode to get, basically it's the whole like type-checked Scala tree that we put in the bytecode so that we can put it out when we like when we use a library. Like when you use a library that was compiled by Dotty, you basically have the whole source code type-checked in your class files, which means that you can do all the optimizations that you really want to do on it.
How is the Dotty faster than the Scala C? I mean, like, why it's faster?
Why is Dotty faster?
Yeah.
We don't know. We actually haven't done much performance work at all. The Scala C people actually are. Is it actually faster?
Yeah.
I haven't actually done benchmarks myself, so I'd rather not say anything that would be wrong. On some code, it's definitely faster, but we'd have to do a lot more benchmarks to actually have a good idea. But we're planning on, at some point, spending time on like getting it to be faster. One thing that Dotty does, that Scala C does not do, is fusion of phases, and I'll talk about that later.
Because I was talking with Martin Onderski a few years back in Scala Exchange, and he promised me that the Scala is going to be faster.
Yeah, so definitely,
That will be.
definitely one of the goals of Dotty is to make Scala faster to compile. I think everyone wants that. Also, if you're interested in performance, like probably Scala 2.14, so Scala 2.12 is not released, but will be released very soon, but Scala 2.14 the developers will try to spend time to improve performance. So you might get performance before Dotty. We'll see how any of that goes. Like performance tuning, it's sort of a black art, and so compilers are pretty hard to tune to get, because they do so much stuff everywhere.
Yeah, you need a big code base to do that actually.
That too, yes. So if you're on JVM,
Current code base is Dotty. Is there anything else? Sorry for kind of like,
you mean
something. Like, what's the Dotty code base right now?
the Dotty code base is
Besides the Dotty.
50,000 lines of code, more or less.
But do you have kind of like libraries or anything else?
We compile most of the standard library of Scala C.
Oh, really?
Yes. Most of the collections, actually. We haven't tried other stuff, because the collection is where all the crazy stuff with F-bound types, recursive types, and complicated class hierarchies are. And I think we compile that faster than Scala C so far. Okay, so let's get into some more details. How do we represent things in the compiler? So basically, we take code and we represent that using trees. Then we attach types to those trees for type safety. And a type might refer to something, an identifier that comes from a source or class file or something. And to that, we corresponds a symbol. A symbol comes from a symbol table, which depends on the current scope. And basically, each phase of the compiler, as I said, will take your trees and your types and simplify them until you can express them using Java bytecode or JavaScript. Turns out, it's similar kind of things. And all of this is immutable, or looks immutable, because actually we do a bunch of caching of things because you don't want to recompute things. So parser is the part that takes your source file and gets you an untyped tree. So if you have some code, with, like for example, obj.fun5, so the parser is going to look at that and see that you're referring to some identifier obj. So the tree that corresponds to that is just an ident tree. And then you're selecting something on it. It doesn't care if it's a method or a value or whatever. So you get a select tree which takes your obj and select your method on it or your value. And then there's an application. And in the application, you have 5, which is a literal. And that's what you get. Once you have this untyped tree, you have to actually type check it. So briefly and very simplified, the way that works is that you're going to go recursively down your tree and type check your subtrees, remembering the expected type. So if you have something like obj.fun5, where you don't know what the expected type is, the first thing you're going to do is to try to type. So type checking is, we use this word interchangeably. We're going to type obj.fun, but at this point we know that this should be a function, something that takes something and returns something else. And to do that, you first need to type obj, and at this point you know that obj has to have a method fun that takes something and returns something. So that constrains what you can do and cannot do. So once you're done, you go back up. So you assign a type to obj.fun based on, like, you're going to look up fun inside obj, and so you have type checked obj. Then you type 5, and at this point, for things to type check and to not get an error, you check that the type of 5, so int, is a subtype of whatever fun takes as a parameter type. And finally, you assign a type to obj.fun5 based on what's the type of obj.fun and based on 5. So what's the expected type business for? Basically, if you have ever tried to compile anything with Scala and it told you like given type something, expected type something, and an error, that's what was going on. We care about expected type because we need to do type inference very aggressively. So I have actually a whole talk on type inference. So if you're a super fan of type inference, definitely look into that. And if the actual type does not match the expected type, we do a bunch of things. We do eta expansion, we do implicit conversions. So to be able to do these things at the correct moment, we need to track what are we expecting. And when that fails, we just say that we have an error, replace the type by an error, and go on. Symbols. So I talked about symbol, but didn't really explain what a symbol is. So a symbol is a definition in a scope. So if we look at the code here, we have the symbols we have are a, foo, and x, because those are all things which are defined and that you might refer to later. So like in the body of the method foo, we call x, and to be able to do that, we need to know where that x comes from. So you need a symbol for x in the scope of the method. So what's the type of the symbol of x? We can just assign t as a type to x in the compiler because everything is immutable. Symbols and types are immutable. But as we go through the compiler, we are transforming things, and after erasure, we don't have t anymore because t is a type parameter, and type parameters don't exist on the JVM, so we replace t by object. So we can just assign t to x, and we want things to be immutable, so we don't want to have to change the assignment. So what's underlying this, and one of the most important concepts of a compiler, is that we need a way to represent time. Because each phase of a compiler is an instant of time. And we have this class which is a period which represents an interval of time. So for example, you might have something, a type or a tree, which is valid between after type checking but until erasure. So that's an interval of time. So you need a way to say that something is valid for a certain interval of time, and when you go past that interval of time, you need to recompute it. So a symbol does not have a type. Instead, it has something which is very specific to Dotty, which is called a denotation. Denotations are circular linked lists of lazily computed types. This is as brief as I can explain them, but maybe not very enlightening like that. Basically, your denotations represents a type, and at some point in time. So if we go back to this example, x at some point in time, like after type checking but before erasure, has type t, and foo has type t to t. So the denotation of x is something which has type t and which has a period like front-end to erasure, typer to erasure. So if you go past that in the compiler, the denotation is going to check the validity field, like the period field, and if it sees that it's not valid anymore, it's going to call the corresponding function in the phase to do the type computation. And so this is done lazily. Why lazily? Because not all denotations are needed at all periods. So your type checking might need to go look into some complicated class file somewhere in your Java class path. And then after erasure, you're never going to look into this again. So you don't have to do any transformation based on this thing. So this linked list is lazy. It's also circular. So I should have added some arrow that goes like this. It's circular because sometimes you need to go back in time. Which sounds very cool and also is very useful because basically when you're at the end of your compilation, like you're in the backend and you're going to generate your code, you might actually be interested in what were my type parameters back when I first type check my code, because that's the thing that you can annotate in your JVM bytecode. So you need some way to say what was the type of this thing back in time. And so the implementation, you just go through the lazy list and go through the linked list and go back to the first thing.
Is it actually implemented with streams?
Sorry, no, it's implemented using like just values, and it's a hand-rolled implementation of a linked list.
Yeah, because there is a stream which is lazy linked list.
It's not implemented using a stream. It's all done by hand. We don't actually use much of the standard library in Dotty. We use lists. We use sequences, we use maps, but we don't use any other complex types. We may use streams for some things I don't actually know, but not for that. For that, we do it by hand.
Yeah, it sounds just like this.
Yeah, it's actually pretty similar to, you could maybe do it with streams. Except streams, can they loop?
I think so, because it's just a function which calls when you need to.
Yeah, you can get streams to loop, but you can do it efficiently, I think, because you have to recompute values every time. So, so this is like the most fundamental structure of the compiler, and it has to be very, very, very fast. Yes. Yeah.
Would these denotation rings be attached to each term in the AST, or are they sort of a separate data structure from the syntax tree?
So the tree, to each tree corresponds a type. This is immutable. And to each symbol, there is a denotation, and some types also have a denotation, but tree themselves don't have denotations. I go in more details in just a second. So there is one last concept about the returners of the way we represent types that is fundamental to Dotty. It's references. So suppose you have just some class A with a type parameter t and some lm which has a type list of t. What's the type of x.lm? It's list of int. But how does the compiler know that? It can just look at the symbol. So the symbol is lm, but its type is list of t. But you want list of int, not list of t. So you can just use the type of a symbol. You want the type of lm as seen from the prefix x. So you want list of x.t, where x.t is just int. And so this as seen from thing is a pretty fundamental thing to how Scala is defined. And every time you have some prefix and some thing inside, you need to look at the thing inside as seen from that prefix. So this is why we have references. There's two kinds of reference, like a reference to a term and a reference to a type. Like you can have x.lm, but you can also have x.t. And those are types. So the type of x.lm is just a term ref of term ref without a prefix. You select X and then you select LM. So this looks a bit weird because like that doesn't really tell you anything about the actual type of a thing. So every reference has a denotation. Whoops. And the denotation is the thing that has the underlying type. So in the same way that symbols have a type. Hello. And that's it for the front-end part. I don't know how much time I still have.
You have a full hour if you want.
Okay. Well, I don't know if people want to hear me for a full hour, but I have less than a full hour of material. I'm going to speak briefly about the middle end. So basically we have the front end and the back end, and the thing in the middle, I decided to call the middle end because I didn't have a good name for it.
Middle end.
So the middle end is the part where you have your shiny type check tree, and you have all your crazy Scala types, and you're going to simplify all of that down until you get to basically Java, but not really Java, but something that you can represent on the JVM. So here's an example of a transformation. If you write T star in your code, at some point we're going to transform that into a sec of T. And when you have, so it's T star is a repeated parameter, and if you have some method foo that takes repeated parameters like 1, 2, and in the same transformation, this time on tree and not on types, you're going to replace that by a call to the sec constructor on foo. So how do phases work? So the traditional way phase work is that each phase is a full traversal of the tree that represents your code. So here's a pretty diagram of a tree. So you could imagine that the top is something like plus and the numbers are 1 and 2 or whatever. And you're after the end of the first phase. And now you're going to do a phase that is going to transform this thing. So the way it works usually is that you do things recursively. So you start from the top, and you're going to recursively apply the transformation to the children. So you're going to transform your first leaf and your second leaf, and once you're done, you transform the parent. And you do that again for every transform. So this is fine, but it means that you need to fully traverse the full tree for every phase. And it's not the actual computation which is the problem here, but traversing a tree is costly in terms of memory access, because a tree is not a single block of memory. It's a thing that points to things which can be anywhere in memory. And every time you traverse the tree, you're going to blow your cache, because your cache is smaller than the size of your tree. So you're going to have to reload things into cache every time. So the mini-phase design that Dotty uses is based on the observation that you don't actually need to fully transform a tree to start another transformation. So suppose that I'm at the leaf, and I transform my leaf from phase 1 to phase 2, then I'm going to also transform it to phase 3. And I'm going to do the same on the other leaf. And now, the parent has to work under the assumptions that the children have been transformed by the transform itself, but also by other transform in the same group. So you can't take everything in the compiler and do that, because you're going, like, things just stop making sense at some point. But if you take small groups of phases that do different things, which are mostly orthogonal, then they can operate in that way and just do their transformation without caring that other phases have done other transformation on children. Okay, so that's it. And as a last thing that I can do, if I still have time, is actually show you how we work on the compiler by trying to fix a bug in real time. I found a bug yesterday, and I think I know how to fix it. I can show you a bit how we look at things and how we debug things. But before that, we can probably answer questions. Any question? Yes?
You haven't told anything about type constructor and how...
Sorry?
You haven't told anything about hard-coded types in Dotty.
Yes.
New syntax for type constructor. Maybe you
So higher-kinded
show some examples.
higher-kinded types in Dotty work pretty much the same way that they do in Scala C. We have implemented some of the stuff that is coming to Scala 2.12, so partial unification of higher-kinded types. So if you have some type parameter m bracket underscore, and you have some actual value of type, for example, int, it can match int with m underscore by setting m equals to int x, where x is the unknown. So partial higher order unifications, which some people are really excited about in Scala C land. And the way it works in Dotty is pretty similar. We have also implemented type lambdas. So in Scala, you can make type lambdas. So a type lambda is a thing that takes a type and return a type. For example, list takes a type and return a type. So list bracket int is a type. And you can make your own type lambdas in Scala, but the syntax is a bit cumbersome. You have to use refinement types and projections. So in Dotty, we added a syntax which is kind of similar to what exists in the macro, which is called kind projector. So I guess I can show an example if I can remember how to do things.
Those changes are for Scala 2.x or only for Dotty?
The higher candidate type syntax?
The same as kind projector.
Yeah, so that's only in Dotty. That might be something
It's
that...
only in Dotty, right?
Yeah,
No.
that might be something that will be implemented in Scala C at some point. I don't have a good example here, but I can show you basically how working on the compiler feels like. I'm going to try to do a short demo of that.
One question about
yes?
kind of types. So type lambdas, not type lambdas, curried types was not a part of SI 2712, but are type currying, is that a potential goal of Dotty as well?
So by type currying, what do you mean exactly?
Being able to specify partial application of type constructors without kind projection. I guess like defining a type lambda with a type projection or with a kind projection inside of it. So you're allowing multiple type.
Yes, in fact that was fixed like 2 days ago or something. Do you have actually a use case for that?
I did, and I can't come up with it, but I used it like 2 weeks ago.
So yeah, we do support that now. So go do exciting things with it, I guess. All right. So let's see if I can do some live hacking or fail at doing live hacking. If I can get my screen to synchronize. Shit. And like you can ask questions and stuff.
So I have a question.
Uh-huh.
Will Dotty support linear types?
Linear types.
Linear
Interesting.
types.
Interesting question. I don't think anyone is working on anything like that, but I don't think it's impossible. But you have to have someone actually work on that, and that's like not a simple thing. Linear types. That's a whole PhD maybe. I think there were some prototype plugins to do things like linear types.
I've seen like the unique one, right? But I think it suffers from some serious bugs.
I have no idea. There was a paper recently by Philip Haller, who he implemented something like linear types. I haven't actually read the paper. But like there's definitely research being done in this area, so something like linear types might come.
Yeah, actually this was the Dotty was based on this calculus or energy types, and I just wanted to wonder what are the use cases of usually dependent type languages it will be possible to implement with Dotty, for instance, type providers, for instance, to generate types in runtime.
So Dotty, Dot, the things that we sort like the type theory behind Dotty is also the type theory behind Scala itself, just simplified as much as possible. And the fact that we represent things using dependent types is because it's a very unifying concept. But does it mean that in your code you have to use dependent types for stuff?
I think that would be useful to have type providers or...
what do you mean by type providers exactly?
For instance, if you have a database schema and you just compile a program and the compile time it generates a type which represents the records in the table.
Okay. Yes.
Without code generation, it's just a type which is like, generated by the query to the database schema.
So type providers are definitely an interesting thing, but I think that whatever the theory behind your language doesn't actually influence much what you can and cannot do here. Like I think F# has something like type providers.
Yeah, that's why.
So, like if someone, I don't think anyone is doing any research in that area currently.
Okay. And also about the termination, are you moving towards this total functional programming, guaranteed termination of the functions?
So we are adding effects, and in a way you could have an effect that disallows things like recursive calls or So it's not impossible to have some form of total function, but like again.
Compiler can guarantee.
Sorry?
How compiler can guarantee that certain function terminates.
Like again, a very interesting and very deep area of research. So.
Yeah, I just know that some languages guarantee that, and there are algorithms like FITIS.
Yes.
And
so the way you can
moving to this like, more typed things.
Yeah, we haven't spent much time thinking about that. I can't get my unified output, so it might be time to call it off. So thanks everyone. And so if you're interested in trying Dotty or hacking on Dotty, I sent a message to the meetup group with like instructions on how you can try things out. It's getting a bit late, so you might not want to do that now, but feel free to do that anytime. And we have a Gitter channel for chatting with people, so definitely we welcome contributors and ideas and stuff. So if you have maybe a complicated idea for a programming language feature, and if you can describe it in some details, feel free to open an issue on our bug tracker and tell us your idea, and we can discuss that. Thank you.
You want to show how you debug?
It's getting late, I think. Do people want to stay a bit and see stuff? Okay, I am going to need a chair. So this is my awesome SBT prompt. That is just a normal SBT project. You compile code using the compiler that compiles the compiler. So Scala C in that case using compile, and you run the compiler using run. And so if you just do run, it's going to tell you it's going to do stuff, and then it's going to tell you that you need to pass arguments. So anyway, the bug I found recently is a very somewhat obscure thing, but let's open a Scala 2 prompt. So in Scala, you can x.type is a type that represents that like the only value of that type is x. So if you try to do var next.type equals 2, I screwed up. So if you do x.type equals 2, you're going to get an error because x.type is not the same as the type of y. Anyway, so if you have two values, actually, let's use a string. So if you have two different values and use isInstance_of to check if x has the same type as y, you could also do pattern matching, it's the same thing. So x is an instance of y.type. Oh yeah, this returns true because x and y actually have the same value here, but if I do something like bar, then it returns false. So the isInstance of check is more complicated than the JVM instance of check, because on the JVM, these things have the same type. They're both string, but for Scala they're different. And isInstance of will add this more complicated checks. And I was surprised when I saw that Dotty, which is building things right now. I like his BT starting time. Okay, here's our awesome web browser where you have colors. Yeah. But when you do the same thing in Dotty, is x an instance of y.type? You get true, and then a warning, but like ignore the warning. So my question was like, why are we returning true here? So the way we see what the compiler is doing is that we have this thing called xprint, which allows us to print a tree of the compiler. So if you do xprint front end on, yeah, I'm going to have to write a file now.
Well, because you annotated it as a string, and that is this specific type.
Yeah, but isInstance_of should not just look at the type. It should actually, for singleton types like that, it should do an equality check. Yeah. Or it's the way it's worked in Scala 2, and I think that's okay. And I think I already wrote an example. Yeah. So I wrote a program that does that. I have many things like that. Like most of the Scala code I write is just examples of things, more than actual code, just to test the compiler. So anyway, if I do that with xprint frontend, I get the code as it was after the type checker. So the type checker is going to add some types. It's going to transform objects into class with module vals, but we don't care about any of that. We can see that we have this isInstance_of check, which is the thing we want. So what we want to figure out is why at some point this becomes true, what is going on. So if we do xprint all, it's going to print every phase, which is horrible to read because then you have this bunch of things. Recently, Nicolas implemented this cool thing, which is called xprint diff. Okay, I have to actually search for it because I don't. Xprint diff del, which just shows you the difference between every phase. Yes, that's pretty nice. So we can see that after this thing, so the phase is this whole thing. Why is this a huge name? Because we have mini phases which are fused in one phase. So when you're debugging, that's somewhat annoying because you don't know which one of this mini phase actually did your transformation. So when you're debugging, you can go into compiler.scala and change the mini phases to be separate phases. But here, we see that our isInstance_of check has been removed and replaced by true. And if I look here, I see something called isInstance_of evaluator. So it's probably related. So all the transform are in Dotty tools.say transform, but even if you don't know that, you're going to do a grep or whatever. I do grep because I'm old school, and you see that it's defined here. And that file doesn't like being that zoomed up. So this thing does partial evaluation of isInstance_of, so it's going to try to optimize your code to replace isInstance_of, which are not needed, which is fine, but it should not get rid of our isInstance_of check and replace it by true. That's incorrect. So what's going on? So I looked at that earlier, and what I saw is yes. To check, so the scrutiny is the thing you do is instance of on, and the selector is the thing on the right-hand side. And this code, the first thing it does is call erasure on both of those things, which is wrong in our case because x.type is erased to string and y.type is erased to string, so they're the same after erasure, but we don't want this instance of to return true. So something is wrong here. So to check if this is actually the program, I can take this function, so it's functions that transform all the type applications, and then checks if there actually is instance of. And it takes a tree as input and returns the transform tree. So I'm going to disable this transformation and just return the tree without transforming it. Okay, let's try this again. Now we're compiling code again, using the compiler that compiles the compiler, and then running the compiler, and we still have true. So what's going on? Okay, so our test.x instance of y has been replaced by true, but we are in a different phase now. We're in erasure, so probably something is wrong in erasure too. So erasure is one of the most complex phases of a compiler because it has to retype check everything, but you don't have to worry too much about that. The part that erase type is called type erasure. So let's look at what it does for. So is instance of is a type application. So let's look how we erase type application. There's a bunch of things going on. Intercept type apply. Let's go there. I don't have jumping working right now in my Emacs, so bear with me. It's defined in type test. Whatever. Yes, in type test cast. Okay, so this thing normalizes type test and typecast, which I saw replace type test with singleton argument type with reference equality check, which is what we want. We want, basically, we want x.is instance of y.type to be replaced by x, y. And this is what the command says it does, but this isn't actually what it does, so something is wrong. So let's look at intercept type apply. What does intercept type apply do? It has a transform as instance of thing, and transform as instance of is called on the erased argument, which is exactly what we don't want, because y.type is erased to string, but we want as instance of to know about the fact that it's a y.type. So if we just change that to be erased, to be the non-erased argument. Oops. What's going to happen? So if we have singletons. Oh wait. Okay, I know what I'm doing wrong. We are looking at is instance of, not as instance of, so I'm in the wrong. Never mind.
The second one is as instance of.
Yes. Yes, I was in the wrong one. We care about is instance of, so let's not give erasure to is instance of, and now let's look at is instance of. So if we look at is instance of, we see that it has a case for singleton types, like y.type. So it will do the correct thing, right? It just didn't do the correct thing because the argument we gave it was already erased. So it was not a singleton type anymore. So if we just do this simple change, and I haven't tried that yet. In the end, we get, yes, the thing we wanted. Test.x equal test.y. So if we want, we can launch the REPL and check that this does what we think it does. Yes, that's correct. Foo is not equal to bar. Of course, well, to actually fix that correctly, we need to do a bit more work. Because, for example, if you have a list of int, which is and you want to check if it's a subtype, well, if you have something which is a list of int and you want to check if it's a subtype of list of string, the arrays types are going to be different. But you still want to be able to do the optimization while you rewrite it to true, because we don't do special casing for that kind of things. So to do that properly, I need to change the code around a bit. But that takes actually thinking about it. So I think for now that's good. And
do you have unit test coverage problems?
Yes. So the way, well, it's not actually unit tests in a way. We have a bunch of test cases. So we have three kinds of test cases. We have post test, neg test, and run test. So post tests are things that will compile. Neg tests are things that shouldn't compile and give certain error messages. And run tests are things that will compile and run without, and give a specific output. So here, if I want to write a test, I'd write a run test because I have to check the runtime. So, so the way it works is that we need a test with a main method, and this is going to be run. And we can have a check file that checks the output, or we can just, we get an error if an assertion fails, so we can just do assert foo Dotty is instance of y.type bar, and add the test. Of course, to do that properly, you need to test over cases and tricky things and stuff, but that's the basic idea. And then you can use part test, and it's going to run all tests and using as much of your CPU as it can and burning your computer by running everything in parallel. So it's not going to run everything in parallel, it's going to look at how many CPUs you have to not overload things. And once you're done, you make a commit and you send a pull request, and we say, looks good to me, and it gets merged. And that's how we work on the compiler. Thanks.